Hello and welcome back to my favorite people, and thank you very much for watching this lecture video. I'm here with another lecture from organic chemistry. We will be talking about nucleophilic aromatic substitution. Question is, can we have nucleophilic substitution reaction on a benzene ring? In order to have such a thing to be happen, we need to have three things. First, our ring must have a strong electron withdrawing group, and something like NO2. Next one is going to be the living group. We need to have a good living group. And how about chloride, bromide, or iodide? Yes, those are really good living groups. And the last one, position of the living group. Okay, position of the living group versus the electron withdrawing group must be either an ortho or para position. Ortho or para position. So wherever you put the like the electron withdrawing group, for example, let's say we have this. I'm going to put the nitro here and I have a ring. I can put the halide or the living group in ortho positions or in a para position. And for example, let's put it here. And that's going to be a para position. So either ortho or para position relative to the relative to the electron withdrawing group. And in this case, we have our electron withdrawing group. So this is going to be electron withdrawing group. And as you see, in ortho position, we have nothing, and this is going to be the para position, while the bromide, our living group, is in meta position relative to the nitro group. So what will happen if I treat this one with sodium hydroxide, and let's say we are also applying some heat? In this case, I'm going to say no reaction. Why no reaction? Because look to the position of the bromide. Should be in ortho or para, not meta. So this reaction is not going to happen. Okay, so let's talk about the mechanism. Okay, so we know in order to run the reaction, nucleophilic substitution, we need to have a strong electron withdrawing group. Next, we need to have a good living group, and the position must be ortho or para. Why? Okay, why? Let's go after that question. So first step of the mechanism, the nucleophile. Our nucleophile is hydroxide. Is a strong nucleophile. The strong nucleophile will be added to that carbon, and this carbon, it has sp2 hybridization. There is a double bond there. We can break the double bond. And if that one happened, now we will have a negative charge. Let's highlight the negative charge. Okay, so as you see, the negative charge is showing in an ortho position relative to the living group, like chloride, or where this one also is an ortho, and here it will be a para. Now let's talk about nitro group. What's the effect of the nitro group? This is the nitro group. Okay. Nitro group is pulling electron density from the ring. We are creating, a negative charge. Anything that stabilizes a negative charge, it will drop the activation energy. Anything that stabilizes the negative charge, it will drop the activation energy, and it will make the reaction faster. Okay. Now, I added the hydroxide. I got a negative charge. As you see, if the negative charge on ortho or para position, you can rearrange it in a way so that the negative charge is going to be sitting on a carbon that's straight attached to the electron withdrawing group. And what will happen if that one, like if you get such a thing? In that case, you can share the negative charge with the nitro group, okay? With the nitro group. Or if there is no resonance, there is no possibility of resonance thing there. If this one is an electron withdrawing group, because it's so close to the negative charge, it's going to pull it out of the ring, and it will make it more stable. Okay, so the closer the negative charge is to the electron withdrawing group, the more stabilization you will get. And I will get this stabilization only and only when the living group is in either an ortho or in para position relative to the electron withdrawing group. Okay, so if chloride is in ortho position here, in ortho position or in a para position, there is a chance for me to put a negative charge on nitrogen. Okay, like in the transfer the negative charge to the nitro group or to the electron withdrawing group. Otherwise, it's not going to happen. Okay, and so this is the reason we say the living group must be in a position in an ortho or para position relative to the electron withdrawing group, because the electron withdrawing group will find a chance to see the electron, the negative charge, and so close to it and pull it out of the ring. And if that one happens, your system will get lower transition state or more stable transition state, and the reaction will be faster. Okay, so in order to run the reaction, nucleophilic substitution reaction, we need to have electron withdrawing group. In this case, do I have it? Yes. And what's the position of the living group? Is in para position. Okay, so I have them in para position. In that case, the product will be this. Nitro stay as it is. And first step, I get this one, and also OH here. Now what will happen? I will have a negative charge here. Okay. Now this system very soon is gonna let the bromide to leave. The bromide will take those 2 electrons and it will leave the system. So minus bromide. And if that one happened, we get this molecule. Okay, plus Br minus. Okay, so in order to have nucleophilic substitution, we need to have electron withdrawing group in a para or ortho position relative to the leaving group. Now, the question is, why on earth we need this, like electron withdrawing group? What's the purpose of it? Let's check just simply benzene and treat it with OH and see what will happen. The pKa of benzene is 43. Well, pKa of water is 15.7. Oh, let's just simply say 15. And now, technically, this reaction is an acid-base reaction. OH is reacting with benzene, is taking H from it and turning it to water. And we say the reaction is going to shift to the side that has a bigger pKa. Clearly, we are getting smaller pKa. So reaction is not going to favor the former one. And clearly, the reaction wants to go back. That means this reaction is not going to happen, okay? Reaction is not going to happen. So if you take benzene and treat it with OH, no way to get this intermediate. That's not going to happen. You're not going to get this base. This base is super unstable. The second you generate it, it will grab H from the solution and it will turn back to benzene. So this is not the way to get phenol. Okay. Now, if you have chloride or bromide or any good living group and you apply hydroxide plus heat, then you can kick it. You can kick the chloride out of the system and replace it by OH. And why I can get the chloride out of the system by hydroxide, okay, but I can't do it with OH. We said OH, and if we have just OH and benzene like hydrogen, it's not going to happen. But if there is a living group like chloride, it can. And the reason for it is this. OH is going to go after this hydrogen, and it will try to take the hydrogen. That hydrogen, it will give those 2 electrons to carbon, and the carbon, it will let the chloride to take those 2 electrons and leave the system. So technically, this is elimination reaction. Okay, you can call it E2 reaction or elimination reaction. Now, what do I get? In this case, I get this. I get benzene ring that it has a triple bond. Okay, triple bond. And what else? We got chloride. And also, we got H2O. So OH took the H, left as the H2O. Chloride also left the system and turned to Cl minus. Now, what should I call this molecule? This is a benzene molecule. Okay, benzene molecule, but it has a triple bond. And remember this. We said when we have a triple bond, we use this, YNE, to say that we have a triple bond. So this is a benzyne intermediate. I got benzyne intermediate. Now, because I have X's from OH, it can be added to the triple bond. Now, I can add it to any of this carbon. And does it matter which carbon? No, they are identical. So I can add it wherever I want. And let's say we added the OH here. OH is coming with a negative charge. So when you add OH, now you will have a negative charge there. That means that carbon, it will have a negative charge. That carbon now is going to go after acidic H, and it will take acidic H from somewhere. So here we have OH, and now took an H from acidic solvent, and that gave us a phenol molecule. And this is the way we generate the phenol molecule. So in order to have nucleophilic substitution, when there is no electron withdrawing group, we need to have a halide. Okay? We need to have a halide, a good living group, and also we have to use high temperature. Okay, temperature is 350. Okay. Now, last step of the reaction, it says we are adding acid to it. Remember this. Okay. Here we are getting an intermediate that it has a negative charge. So we need to have some acidic, solvent to technically neutralize that negative charge, and that's the reason. And always we treat the reaction at the end with acidic H. Okay. Now, if you use a strong base, like let's say NH2 minus 1, then you can actually drop the temperature. You don't need to use a really high temperature, and you can run the reaction in a milder condition. Okay, so in this case, sodium, it has a plus charge, and this one it has minus 1 charge. So now what will happen? This one is going to go after acidic H, and it will take this. And so what do I get? Now we get NH3, okay, and chloride. So the hydrogen will give up those 2 electrons to carbon, and chloride will take those 2 electrons, will leave the system. So I get chloride also. And then I get this intermediate. Again, benzyne intermediate. Now I have 2 identical carbons. And because I have excess of NH2, it can be added to any of this carbon. Let's say we added the NH2 here. So now we have NH2 here. That means we're going to have a negative charge there. Now I need to treat it with an acid. And the acid is going to give me acidic H, and I will get that one. Okay. Again, I got benzyne intermediate, and now unlike this intermediate, both carbons are identical, so it doesn't matter where you put the NH2. But what will happen if you have a substituent? In that case, you will get different product. And for example, I have parachlorotoluene, and I'm treating it with a strong base, and this is the strong base. It will go after one of these hydrogens. Okay, the hydrogen that is close to the alpha carbon. I'm going to treat this one as alpha carbon, and so it will take that hydrogen. And if that one happen, this one's going to go after hydrogen. Hydrogen is going to give up those 2 electrons, and the chlorine will leave the system again. So we get minus NH3. Next, we will get Cl minus, and here we will get this triple bond. Okay, now I have 2 carbons. Okay, that the base NH2 minus 1, it can reach them. Okay, is there any preference here? Not really, because the methyl group is way far from them. So like we have 50% chance to reach any of those carbon, because there is not much steric effect here. And if that one happen, okay, then okay, I can here when I add the NH2 to it, it can be added. Let's say it can be added to this carbon or that carbon. Okay, and again we have a triple bond here. Okay, and so let's say we added the NH2, for example, in one case here, another case we added NH2 there, and I'm going to treat it with acidic H. Acidic H, it will be here and there. Okay, and so as you see, we got para product, and this one we got the meta product. Why did I draw this one that way? Okay, so we have para and meta product, and what's the ratio for them is going to be 50-50, because the methyl group is not that bulky to generate too much steric effect. Okay, and this is the reason why whenever we treat parachlorotoluene with a strong base, we get 2 products, because we get a benzyne intermediate, and that intermediate, it has 2 almost like identical carbons, and yes, their position relative to the methyl group is different, but they will not really, you can't differentiate them by steric effect. And so when the nucleophile wants to reach them, and it has 50% chance to reach either of them. Okay, and that's the reason I get such a product. And this is going to be the end of this lecture, and thank you very much.